Hi, this is the second part of the lesson we're doing on calculating radiometric ages. And in particular, this time, I want us to work out the age of the Bodmin Granite in Cornwall. As last time, you're going to need your A3 calculating the age of the Bodmin Granite worksheet, and you will need a scientific calculator. Okay. This is the simplified map of Cornwall and part of Devon that we were looking at last time. Just so we know which intrusions we're talking about here, we have Land's End in the far west, followed by Carnmellis, St Austell. That's the Bodmin Granite, and we just see the edge of the Dartmoor Granite. It would be useful if you label up on the geology map you have of Devon and Cornwall on your worksheet which one's which. It'll help you understand what's going on. Okay. Having got our geography sorted, we now need to think more about the geology. This is some data. You've got a black and white version of this, but these are some of the dates for this activity or this igneous activity in this area. There's two dating methods in particular been used for the intrusion of the granites. We do have some data about the mineralization that occurs around these intrusions from Sumerian neodymium dating, but we're really interested in the dating of the granite itself. There are uranium lead dates, which are the dark blue rectangles shown on this diagram. And then there's the potassium argon date, which are shown with the red and orange sort of ovoid shapes. There's an interesting pattern, I think, with all of these results, but perhaps we'll come back to that later. One thing you do need to be careful of with this diagram is the age axis. Unusually in geology, the oldest is at the top, the youngest is at the bottom. So time is actually, or age is decreasing the further down this diagram we look. Okay. Having seen this, what I'd now like you to do is actually work through the questions. So there's question 4 on the worksheet. Use what we learned in the last lesson, how old, and to work out how old the Bodmin Granite is. But work through those questions in sequence. They'll help you do that. Have a go at that now. So press pause and see what you can come up with. Okay. Hopefully now we've managed to come up with some good answers to these questions. Let's go through and I'll show you what I've worked out. So the first question was to calculate the half-life of uranium-235. It's not a technique that you need to memorize, but the same principles apply as it does to the potassium argon dating that you do need to know. So if we put the numbers in the equation, the decay constant there for uranium-235, that's the equation we get. Work through the sums and we end up with a half-life of 704 million years. Now once we know the half-life, we can see that this technique is actually really useful in terms of dating most geological events. You know, it's long but not massively long. If we look at the Bodmin Granite itself, we've got a ratio there that's been measured, the parent of 22,000 isotopes the daughter of 7,172 isotopes. If we put that into our equation, so we're just substituting numbers. Key to this, I think, is to work it out in sequence. So we do our brackets first, then we do the natural log. So we then have a simple division to do at the end. Don't try and do this all in one go on a calculator. Okay, break it down. You'll pick up marks for doing it, and it avoids errors with typing things in. Okay, this is what I've done with this. So we get a natural log of 1.326. That gives me that sum, and gives me an answer then of 287 million years. Breaking it down like that makes life easier for you. It stops you overcomplicating things. Unless you're really confident with the maths, break it down. Okay? Having worked out the age, our next step is to work out the range of ages it could be, because all of these dates come with errors. The error in this particular case is estimated to be 1.4%. So if I multiply my date by 0.014, which is 1.4%, gives me an error of 4 million years. So the age of the Bodmin Granite must be 287 plus or minus 2 million years. This gives that 4 million year window. To plot that on the graph then, we end up with an answer that looks like that. So once we've worked out the date, we can then start to see how these fit into the pattern within the area. So if we look at our geology map of Devon and Cornwall, we can start to rank these the intrusion of these granites. Remember, of course, that the oldest event is at the top of this graph. So we can see that Carmelis is the oldest, followed by Bodmin, followed by St Austell, followed by Dartmoor, and finally then the youngest one is in Land's End. But you can see that there's these plutons are still fairly similar in age. There's about a 15 million year window of time in which these things were actually forming. So they're clearly part of the same event. This event is the Variscan orogeny. These granites are a direct result of Britain becoming part of Pangaea. The plate collision, which happened just to the south of Britain in northern France, generated magma, which intruded the rocks in what's now Cornwall and Devon. Okay. Final question then was to evaluate the dating techniques that are used. Okay, looking at the emplacement of the granites. And I think there's a really interesting pattern here. Because if you look at the potassium-argon dates, compare them to the uranium-lead dates, all of those potassium-argon dates are younger than the uranium-lead. Now, does this go back to the potential error that we talked about when we're looking at potassium-argon, with the fact that the daughter product in potassium-argon is a gas, and that gas can be lost from the minerals. If that gas is lost, it inevitably will increase the proportion of parent atom and make the rock seem younger than it actually is. You know, clearly this isn't a random pattern of error. Clearly there's a systematic change. With uranium lead, chances of lead escaping from a crystal lattice is much, much lower than it is for argon. Okay, as we look at sunset over Bodmin Moor, with conclusions, of course, in Cornish, let's just adjust that. These techniques allow us to put an accurate date onto a rock. Once we've got an accurate date, we can start to piece together a bigger geological picture, like putting the intrusion of these granites into the context of the Etruscan orogeny, and actually being able to date that plate collision really quite accurately. This is a technique that can be applied in really any part of the course, even in the quaternary geology, where we're dating maybe ash layers in a sequence of fairly recent sediments.